Everyone, my name is Nikita. I am from EC branch. My subject is MTT and my topic is half-line sine transform. First, we have to know what is transform. In mathematics, a function that results when a given function is multiplied by a so-called kernel function and the product is integrated between suitable limits. F of s is equals to L of f of s is equals to integral of 0 to infinity e to the power of minus st into f of t into dt can be thought of a suitable substitution. Fourier sine transform. Similar to the Fourier cosine transform, the Fourier sine transform of a function f of t, which is piecewise continuous, and absolutely a function f of t, which is piecewise continuous and absolutely integrable over 0 to infinity, is defined by application of a operator f as f of h equals to f of t is equals to integral of 0 to infinity f of t into sine omega t dt. The inversion operation of f is similarly defined as f of omega is equal to 2 by pi integration of 0 to infinity f of omega into sine omega t into dt. Here we can see the problem of Fourier sine transform. Fourier transform. Property of transmission. They convert a function from one domain to another with no loss of information. Fourier transform. F of omega is equals to 1 by under root 2 pi integration minus infinity to infinity f of t e to the power of minus omega t dt. Converts a function from the time domain to the frequency domain. A Fourier transform is a mathematical transform that decomposes a function depending on space or time into function depending on spatial frequency or temporal frequency. This process is called analysis. An example application would be decomposing the waveform of a musical chord into term of the intensity of its constituent pitches. The term Fourier transform refers to both the frequency domain representation and the mathematical operation that associates the frequency domain representation to a function of a space or time. Here is an example of Fourier sine transform. An example application of Fourier transform is determining the constituent pitches in a musical waveform. This image is the result of applying a constant Q transform to the waveform of a C major piano chord. The first three pitches on the left correspond to the frequencies of the fundamental frequency of the chord. The remaining smaller peaks are high frequency overtones of the fundamental pitches. A pitch detection algorithm could use it to relate intensity of these peaks to infer which notes the planet pressed. The Fourier transform of a function is a complex valued function representing the complex sinusoids that comprise the original function. For each frequency, the magnitude of the complex value represents the amplitude of the constituent complex sinusoid with that frequency, and the argument of the complex value represents that complex phase offset. It is a frequency is not present, the transfer has a value of 0 from that frequency. The Fourier transform is not limited to frequency of time, but the domain of the original function is commonly referred to as the time domain. The Fourier inversion theorem provides a synthesis process that recreates the original function from its frequency domain representation. Transform with the cosine and sine function. The function kernel represents an important area of analysis. It is based on this so-called half-range expansion of a function over a set of cosine or sine basis function, because the cosine and the sine kernel look lack look the nice properties of an exponential kernel. Many of the transform properties are less elegant and more involved than the corresponding ones for the Fourier transform. In particular, the convolution property, while it is so important in many applications, will be much more complex. Here you can see the diagram. The red sinusoid can be described by a peak amplitude, peak to RMS, and the wavelength. The red and blue sinusoids have a phase difference of theta. The top row shows a unit pulse as a function of time and its Fourier transform as a function of frequency f omega. The bottom row shows a delayed unit pulse as a function of time g of t and its Fourier transform as a function of frequency g of omega transform, that is delay in the time domain is interpreted as complex phase shift in the frequency domain. The Fourier transform decomposes a function into a eigenfunction for the group of transform. The imaginary part of g of omega is negated because a negative sign exponent has been used in the Fourier transform, which is the default has derived from the Fourier series, but the sign does not matter for the transform that is not going to be reviewed, that not going to be reversed. Functions that are localized in the time domain have Fourier transform that are spread out across the frequency domain and vice versa. A phenomenon known as the uncertainty principle. The critical case for the principle is the Gaussian function is of substantial importance in probability theory and statistics as well as in the study of physical phenomena exhibiting normal disturbance. Example, diffusion. The Fourier transform of Gaussian function is another Gaussian function. Joseph Fourier introduced the transform in his study at heat transform when Gaussian function appears as solution of the heat equation. Basic properties and operational rules. Inverse transform. The inverse transform is exactly the same as the forward transform except for the normalization constant. Combining the forward and inverse transformation leads to the Fourier sine integral formula, which states that f of t is equal to 2 of pi integral 0 to infinity f of omega of sine omega t d omega is equals to 2 pi integral 0 to infinity in the bracket 0 to infinity f of t into sine omega t dt. Back in the bracket and sine omega t into d omega. The sufficient condition for the inverse formula are the same as for the cosine transform where f of t has a jump discontinuity at t is equals to t0 converges to the mean of t of f of t of 0 plus 0 and f of t of 0 minus 0. Transformation of derivatives. Derivation transform is a fashion similar to Fourier cosine transform. Even orders involving sine transform only and odd orders involves cosine transform only. Complex Fourier transform. An earlier module we showed that a square wave could be expressed as a superpositional of pulses. As useful as this decomposition was in the example, it does not generalize well to other periodic signals. How can a superposition of pulses equal to smooth signal like a sinusoid? Because of the importance of sinusoid to linear system, you might wonder whether they could be added to linear system. You might wonder whether they are added to whether they added together to represent a large number of periodic system. You would worried about this problem, and Jean Baptiste Fourier got the credit, even though mathematical issues were not settled until later. They worked on what is now known as a Fourier series, representing any periodic signal as a superposition of sinusoid. The Fourier transform of a function complex valued function representing the complex that comprise the original function. For each frequency, the magnitude of the complex value represents the amplitude of a constituent complex with the frequency, and the argument of the complex value represents that complex phase offset. It is a frequency is not present, the transform has a value of 0 that frequency. The Fourier transform is not limited to function of time, but the domain of the original function is commonly referred to as the time domain. The Fourier inversion theorem provides a synthesis process that recreates the original function from its frequency domain representation. The complex form of an Fourier integral of any function f of x is in the form f of x is equals to 1 by 2 pi integral minus infinity to infinity. Here is the two integrals. We can use it two integrals. Again, minus infinity to infinity f of t into e to the power of I lambda of t minus x into d lambda dt. Replacing lambda by x, f of x is equals to 1 by 2 pi integral 0 to infinity e to the power of minus sx ds integral minus infinity to infinity f of t into e to the power of minus st into dt. The real and imaginary part of the Fourier coefficient are written in the unusual way for convenience in defining the classic Fourier series. The zeroth coefficient equals the signal's average value and its real value for real valued signal. C0 is equals to A0. The family of function e to the power of I 2 pi 2 pi kt by t are called basic function and form the foundation of the Fourier series no matter what the periodic signal might be. These functions are always present and form the representation building block. They depend on the signal period t and are indexed by k. Thank you.